Hi, thanks for joining me. Today I'm going to be talking about Fermat's last theorem and some Fermat near misses. So firstly, what is Fermat's last theorem? Well, you've probably heard of it, but if you haven't, let's quickly go over it. It considers this equation here, x to the n plus y to the n equals z to the n, where x, y and z and n are positive integers, natural numbers, and n is at least 3. The theorem says that there are no solutions to this guy here. Now this took quite a while to prove, over 350 years, by Andrew Wiles back in the 1990s. And in fact, I made a kind of joke video in which I prove Fermat's last theorem in just like 5-10 minutes. But obviously that proof is a false proof. Anyway, what I've written on this line here seems to contradict Fermat's last theorem.
Homero, te habla tu médico, el doctor Julio Hibbert. ¿Puedes decirnos cómo es ahí?
Es como... ¿Alguien vio la película Tron?
No.
No.
No. No. No.
No.
No. No. No.
No.
Sí. Digo, no. No.
1782 to the 12 plus 1841 to the 12 equals 1922 to the 12. And in fact, if you plug this into your calculator, it will seem like this is true. But in fact, it's not true. The only reason it will appear true on your calculator is because we're working with extremely large numbers here, so there are going to be some rounding errors in your calculator. And you can actually kind of see that this is not true, because this here is an even number, this is an odd number, and that's an even, and you can't have even plus odd equals even. But this appears to sort of contradict Fermat's last theorem, and it's what we're going to call a near miss. I'm deliberately not defining what I mean by a near miss of Fermat's last theorem, mainly because there are a lot of different ways you can define it, but it hopefully is quite clear to see what we're trying to aim for, that we want to find sort of x, y and z positive integers and n a positive integer at least 3, such that x to the n plus y to the n approximately equals z to the n. Anyway, in this video I'm going to be showing you a way you can generate these Fermat near misses. Okay, so let's get stuck into generating some Fermat near misses. The first thing we're going to do is just consider some positive integers p and q, such that p is less than q. So then we have that 0 is less than p over q, and that's less than 1. Then what we want to do is just consider 1 minus p over q to the n, and then the nth root of all of that. So 1 minus p over q raised to the n, and then all of that raised to the power of 1 over n. And this will be some number. We don't know what that number is, but I'm going to call that number, let's call it t for now. Why not? And now you can actually prove that t is going to be an irrational number, because if it was rational, then you'd be able to contradict Fermat's last theorem just by rearranging this. So it's irrational, but we can approximate irrationals by rational numbers. So if you've not seen this before, it essentially comes from the fact that the rationals are dense in the reals. So for any real number you choose, you can always find a rational number arbitrarily close to that irrational number that you initially chose. Okay, I'm not going to prove that in this video, but that's kind of a standard fact about the real numbers. Anyway, so we can approximate this with some rational number, which I'm going to call a over b. And we can make a over b as close to t as we want, and that's kind of important. And a and b here are just positive integers, so we have 1 minus p over q to the n raised to the 1 over n is approximately equal to a over b. And now what we're going to do is just rearrange this guy here. First thing, raise both sides to the power of n, so we get 1 minus p over q to the n equals a to the n over b to the n. And then we're just going to sort of multiply through both sides by b to the n times q to the n. So this side becomes bq to the n. Oh, I should probably put an approximately equals to here. Bq to the n minus bp to the n is approximately equal to aq to the n. And then just adding bp to the n to both sides, I'm going to get rid of this from this side and put it on this side. And now we've found sort of an approximation to Fermat's last theorem, or an approximate solution to Fermat's last theorem, or Fermat's equation, which says that there are no solutions to that equation, but we found an approximate one. aq to the n plus bp to the n is approximately equal to bq to the n, and these of course are all just positive integers, and n is some positive integer at least 3, and this is kind of cool. Like we know that, or by Fermat's last theorem, there are no solutions to x to the n plus y to the n equals z to the n, but we can find approximate ones quite well. And notice I haven't said what P and Q and A and B are. Well, A and B are kind of dependent on P and Q. But P and Q, you're free to choose any positive integers you want. And then you get this nice approximately equal to here. Okay, before I end the video, I'll leave a little homework exercise for you guys, is to consider this sort of bit of here, this bit of the proof here, where I had t is approximately a over b. So t is an irrational number, this guy here, and I've approximated it by a rational number. But you may ask yourself, why do we need to approximate? We can actually make it equal to, and then just provided we add on sort of the remainder. And we can, because the rationals are dense in the reals, I can make this epsilon be as small as I want by making my rational number be as close to t as I want. Then what I will encourage you to do is kind of go through the steps and then see why it becomes a little bit difficult to then define what a Fermat near miss is. And I deliberately, in the intro, avoided defining a Fermat near miss exactly because of this. So yeah, do have a play around with what happens when you write it like this, and then, you know, essentially just crunch through the computations and the rearranging again, and then see if you can spot the issue. And there's actually a lot of cool maths that has been gone into this area, but I'll let you explore that for yourselves. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.